Hi everybody, I hope this video finds you well. In today's video, we're going to be moving on into chapter 11 of your textbook, starting with section 11.1. Chapter 11 is sort of the introduction into our next major section of our course. The previous couple sections that we've been doing, chapters 6 and 7, have really been focused on integration, either learning different applications of definite integrals, whether those be areas, volumes, average value, work, etc. Or in chapter 7, we spent more time learning techniques of integration. How do you actually come up with different antiderivatives for more complicated expressions? Sort of towards the end of chapter 7, though, we started to really get closer to this idea of accumulating infinitesimally small pieces. And we saw that through the lens of what we called improper integrals. Improper integrals, we sort of were dealing with these sometimes infinitely long but infinitesimally thin areas and trying to decide if that came out as a finite area, an infinite area, and how to sort of analyze that type of question. In chapter 11, we're going to be continuing that sort of investigation about accumulating things. But to do that, we're going to change gears a little bit away from sort of continuous functions to discrete collections of things. So to start off with, even though sequences are not going to be one of our main pieces of study, to be honest, we have this one section, section 11.1, that deals with sequences, and then the remainder of section 11, or of chapter 11, deals with series. But sequences sort of form the foundation of helping us understand series. So we've got to do a little bit of work to just understand what a sequence is and how we analyze them. So let's begin just to start off with a very basic sort of definition. A sequence is simply a collection of mathematical objects. For our class, that's pretty much exclusively just real numbers, organized by an index of discrete whole numbers. So in other words, a sequence is sort of a discrete collection of mathematical sort of objects. For us, it's just going to be a discrete collection of real numbers. And it's organized by an index, meaning that we know what the first element is, what the second, what the third, so on and so forth. So to start off with, before we get into any sort of analysis or anything, let's just go ahead and take a look at some examples of what a sequence sort of looks like, how we define it, and what it really means. So here's some example sequences. Our first one is a sub n equals 1 over n plus 1. So how you can think about this is you can basically think that this formula, this is sometimes referenced as an explicit sequence because it gives us an explicit formula for what each element of the sequence looks like. So in this case, you'll notice that this tells us that the sequence runs for n greater than or equal to 0. So we start with the index at 0. So we would have a sub 0 here. If we plug in 0 for n, that's why we have a sub 0 here. And then we'd have 1 over 0 plus 1. So we'd have 1. And then we'd have a sub 1. We'd plug in 1 for n, and we'd have 1/2. And then a sub 2 would be 1/3. And then a sub 3 would be 1/4, and so on. If you didn't want to write a0, a1, a2, a3 each time, of course this continues on, you could also use like a sort of set notation and just say it goes 1, 1/2, 1/3, 1/4, so on. And these, for us, sequences continue on indefinitely. So you can already probably guess what we're going to be interested in the long run. In the long run, we're going to be sort of interested in where do these things head. And in this case, you can probably guess what this is sort of tending towards. Since these fractions are getting smaller and smaller, we might try to use a concept like the limit to say that this sequence eventually tends towards 0. And in just a few minutes, we'll actually be able to make that definition formal. But the things I want you to sort of realize here is that unlike almost all of your calculus that you've done so far, which has always been with continuous functions, things here are discrete, meaning that we have 1 and then we go to 1/2, then we go to 1/3, then we go to 1/4. There's nothing in between, right? The sequence is a discrete collection of numbers. So there is nothing in between these. We just have these moments where the index is at these whole number values. All right, here's another one. B sub n equals n over n plus 1 to the n. So this one's a little bit more complicated. Notice also this one starts from n greater than or equal to 1. At the beginning, we'll sort of pay attention to this, like where it starts from. But to be honest, it doesn't matter that much because, like I already sort of hinted at, we're going to be much more interested in the long-term behavior, not what the starting behavior is. But in this case, we'd have b sub 1, which looks like it would be 1/2. And then b sub 2 looks like it would be 2/3. and then squared. So I guess that would come out as like 4/9. And B3 would be, if we plugged in 3 there, it looks like it'd be 3/4 sort of cubed. So it looks like that'd come out as like 27 over, say, 64. And I don't know if we just wanted to do one more. B4 looks like that would come out as 4/5 to the 4th. So I guess that would come out as like 256 over like 625 or something. Again, we don't really care about the arithmetic, but there we go. So if you didn't want to write all that out like that, you could use those sort of set notation. So this is the sequence that goes 1/2, then 4/9, then 27 over 64, then 256 over 625, and it continues on from there. Remember, these things always keep going because the index, right, says that they just, as long as the index is greater than or equal to 0 in the first one or greater than or equal to 1 in the second one, these just continue on. Okay. Here's a third example of this. Notice that this one, right, you can involve functions just like you would normally be able to. So here we'd have C4 would be the first one, which would be ln of 1, which would be 0. And then C5 would be ln of 2. And then C6 would be ln of 3. And C7 would be ln of 4. All right, so this would be the sequence that goes 0, ln of 1, or sorry, ln of 2, ln of 3, ln of 4, and then just continues on forever like that. Now, as I sort of said, in just a few minutes, we're going to sort of state what we're really going to be interested in, which is going to be the long-term behavior of these. Notice that just from this one, we could probably guess that this is going to tend towards 0. It'll never quite get there. We'll always have 1 over some massive number down there, but eventually this is going to get very close to 0. This one might be pretty hard to analyze, right? Because so you can't really see an easy pattern here. But this one should also be pretty easy. This is just going to be ln of larger and larger numbers. This is probably just going to keep getting larger and larger. This is probably headed towards somewhere like positive infinity. So, your ideas that you've already understood about how sort of limits and things work, we're going to see that they parallel with what we're doing with sequences here. Just the big idea again is that sequences are discrete. There's nothing in between these. The sequence itself is just each of these discrete values. Okay, for a very special type of sequence, something we're going to investigate a lot in the sort of second half of 11.1, so in the second video for 11.1, are things that are not explicitly defined equations. For these first three, like I sort of mentioned, we could call these explicit sequences, because if I want to know any one of the values, all I need to do is just plug in n. Notice if you were interested, you could figure out like what is a sub 100. It would be 1 over 101. Or if you wanted to know C sub 1000, it would be ln of 997, right? You have an explicit formula that tells you wherever you are in your sequence, you just plug in, that gives you the value at that moment. This is often referenced as an implicit sequence, or sometimes a recursive sequence, and that's sort of the name we'll give. The reason that it's called a recursive sequence is that it doesn't give an explicit formula. Instead, it tells you where you're starting from and how to move forward. So let's see how we would actually determine the first few values in this. So notice that we know that d sub 0 is equal to 1. Then we could figure out that d sub 1, according to this formula, should be the square root. And notice that if n is 1, this subscript would be 1 minus 1, which would be d sub 0 plus 1. And then we could say, okay, well, we know that d sub 0 is 1, so we can plug that in. So it would be the square root of 1 plus 1. So we'd get that d1 is square root of 2. Then to get d2, well, I could again use this sort of formula here, and I could say it's the square root. Notice that if I have a 2 here, then down here I'd have 2 minus 1, so I'd have d sub 1 plus 1. And then I could say, well, I know what d sub 1 is. It's square root of 2. So I would end up with the square root of the square root of 2 plus 1. If I wanted to go one step further, say d3, I could say, okay, d3, use this expression here. It's the square root. If I have 3 over here, then this subscript would be 2. So I'd have d sub 2 plus 1. But, of course, we just figured out what d sub 2 was. So I would have the square root of the square root of the square root of 2 plus 1 plus 1, right? Where I've plugged in d sub 2 right there. That's just this expression popped in there, then plus 1, and then square root it again. So notice that this would get very messy. You would not be a pleasant experience to have to answer what is d sub 100. Because how would you get d sub 100? Well, you'd have to know d99. How would you know d99? Well, you'd have to know d98. You'd have to work your way all the way through every one of the values. Now, it turns out that with some of the sort of theorems that we'll be proving a little bit later on in section 11.1, well, we'll actually be able to figure out if this thing is tending towards some value without actually knowing what it equals along the way. If you wanted to, of course, you could put this in that sort of set notation. This is 1, root 2, root 2 plus 1, and then root 2 plus 1 plus 1. And then so on and so forth. But it will turn out that by the end of sort of the next video, we'll actually be able to analyze the limit of this thing. Where is this thing sort of headed in the long run? Even though we don't have an explicit formula for what d sub any n is. We only know d sub n in terms of the previous one. So these recursive sequences, we won't see them for a little while. Actually, in the remainder of this video, we won't sort of reference them. But when we get into the second half of section 11.1, we will return to sort of investigating these. For now, though, we're going to focus more on these explicit sequences, where we have an equation that tells us what each term of the sequence is equal to in terms of where we are in the index. Okay, so let's go ahead and sort of formalize what we're going to be sort of doing with these sequences. So, as I sort of mentioned, for sequences, we're going to be mostly interested in their long-term behavior. So in more sort of mathematical terms, we're going to be interested in what happens to these sequences as n goes to infinity. So this already tells us one sort of unique thing. While sequences can be a little bit abstract when you're first studying them, in some ways they're a little bit easier because the only question we're ever asking about sequences is what happens as that index tends towards infinity. We're never interested in what happens as the index goes to negative infinity or like 5 or something like that. We're always just letting that n, that index, right, the sort of position that we're in, get larger and larger and seeing what the end behavior is. So the sort of questions that we're going to be answering are always going to be very similar because this is the main question we have for sequences. So we've already sort of hinted at that we're going to use some limit terminology, so we need to give the sort of limit definition here. And if you think back to your sort of Calculus 1 class where you learned like an epsilon delta definition for limits, this definition is very similar. So this says that a sequence a sub n is said to have limit L written using the limit notation, limit n goes to infinity, a sub n equals L, if for any epsilon greater than 0, so for any epsilon greater than 0, there exists a whole number, capital N, such that once your index is past that capital N, the following inequality holds. That the absolute value of the difference between a sub n minus L is less than epsilon. So this basically says that there is some point, some whole number n, such that whenever you're beyond that whole number, capital N, the difference between your sequence and the value of the limit, remember this absolute value just measures the distance there, so the distance between the sequence and the value of the limit is less than epsilon. So very informally, what this definition says is that a sequence has limit L if the sequence at some point gets and stays arbitrarily close to the limit value. A little bit of terminology here. If the sequence an has a finite limit according to this definition, then the sequence is said to converge to L. Otherwise, the sequence a sub n is said to diverge. So just like we were talking about with improper integrals, there's this concept of convergence, which means that you have a finite limit, and divergence, which simply means does not converge. Again, should make that note that diverge is a very sort of complicated idea because diverging simply means not converging. So the sequence a sub n could diverge, meaning that it approaches infinity, negative infinity, or simply that the limit does not exist. So just keep in mind, diverging can mean a lot of different things, or put another way, you can have a sequence diverge in a lot of different ways. It might be headed towards infinity, negative infinity, or the limit might simply not exist. So let's give a quick visualization of this definition here. In your Calc 1 classes, you might have done a lot of sort of little proofs using the epsilon delta definition of the limit. We're not going to really encounter those too much. We'll see one theorem sort of later on that uses the very formal definition here. But what's more important is probably really making sure you sort of understand visually what this definition is really saying. So we're going to give a visualization here. So let's imagine we sort of have a coordinate axis, and we're going to sort of label this as our n here, and we're just going to care about the sort of discrete values. So we have a bunch of sort of discrete values there. Okay, and we're going to say maybe that the L that our sequence is eventually going to approach is right there. And what I'm going to sort of imagine is we're going to talk a little bit about sort of understanding this. So let's let epsilon be greater than 0, and let's go epsilon away from L. So let's take, say up here, maybe this is L plus epsilon, and down here, this is L minus epsilon. And I'm going to sort of take some pieces here. Okay. Okay. So what we're basically saying is, if we're going to say that our sequence goes to this value of L, then it doesn't matter what the sequence does early on. Maybe the sequence starts off down here, maybe it lands in here, then maybe it pops back down here, maybe it shoots way up here, right? Then maybe it pops back in here, then it comes down here for a while, okay? We don't care, right? It's just doing whatever the sequence does, right? Remember, graphing a sequence, because it's discrete, is just going to be graphing a bunch of points. There's no curve connecting them. It's not a continuous function or anything like that. It's just a bunch of points. Okay, but what has to happen, I'm going to extend my drawing just a little bit here, and just to make it sort of clear, is if this sequence that I'm drawing out, this blue sequence, is really going to have a limit that is equal to L, at some point, which we would call capital N, maybe capital N is right here, right? I mean, maybe it's sort of right there. Beyond that capital N, forever onwards, doesn't matter if it fluctuates, but it has to now live in here, meaning that forever onwards, every point, even though it might be sort of fluctuating, is going to now live inside that L plus epsilon, L minus epsilon. Then, if you wanted to make the epsilon smaller, so maybe you want your dashed lines to be even a tighter fit around L, well, then you would slide that capital N further down, and your points would all sort of cluster in there. So the sort of point is, when you're talking about the limit of a sequence, you don't really care what happens over here, right? The sequence can do whatever it wants over this finite sort of set of values. But once you get beyond that capital N, your points stay within epsilon of the limit. And of course, epsilon is arbitrary, so you can squeeze that epsilon even closer together, and then you can move that capital N further down, and your points will cluster inside that smaller range. That's what it means for a sequence to have a limit. So again, doesn't matter what happens early on, you can have all sorts of crazy behaviors, but at some point, this capital N, once you're past that capital N in terms of your index, your sequence gets inside of here and stays inside of here. That's the real idea. Okay, so again, this is sort of the very formal definition with the epsilon and the sort of capital N and everything like that. We will use that later on to prove one theorem, but again, for your guys' understanding, I think it's really important to make sure you sort of have a visualization of it. What would be things that would diverge? Well, it would be if, say, these points kept jumping out. So, instead of sort of all staying in here, we kept having them sort of pop in and out. Maybe some of them are in there, but some are outside of there. If they never all cluster in here, then it's going to diverge because the limit isn't going to exist. Also, if the points just kept getting larger and larger, so there was no range that you could sort of keep them in, or if they kept getting smaller and smaller, those would be examples of things that would diverge to infinity or diverge to negative infinity. So again, when you say something converges, it's a very strict visualization. Your points have to get and stay within an arbitrary bound of your limit. Okay. Next thing we want to talk about is, in terms of analyzing sequences, we're almost ready to actually just start analyzing the limits of sequences. But there's one really sort of important connection that ties together your guys' understanding of limits of functions with this new concept of the limit of a sequence. So We're going to give this theorem a name. In your textbook, it's just written as a theorem, but we're going to give it a name so that we can reference it very easily. We're going to call it the replacement theorem. And the replacement theorem basically is stated as follows. Suppose you have a sequence a sub n, and suppose you have a function f of x. So a sub n is a sequence, and f of x is a function, such that that function matches the sequence for all n defined in the sequence. So in other words, you have a function that matches your sequence for all the whole number values. Then, if the limit as a function goes to L, then you can also conclude that the limit as a sequence goes to L. So in other words, if the function converges, so does the limit. All right, or so does the sequence. So what's our visualization here? Well, it's actually very simple. All this is saying is if you have your sequence, maybe your sequence looks something like that, okay? And you want to understand the behavior of what these sequence values are doing in the long run. Well, if you can find a function, this f of x, and this f of x goes through every one of these points. So in other words, there's some function that connects all of these points together. Then where this function is headed is also where the individual points are headed. And that should make total sense, right? If we can find where the continuous function is headed towards, then certainly these discrete values along the way are headed to the same spot. Now, this hinges on being able to find a function that goes through all the points. If the points exhibit some really crazy behavior, say your points are like here, here, and then here, 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 so on and so forth, right? You might not be able to find a function that does this. So this doesn't say that you can always find a function, a continuous function that matches your sequence. But if you can, then the limit of the function is the same as the limit of the sequence. Okay. So again, just so that we can, if you look back at this, these are your a sub n, and your red is the red curve here is your continuous f of x. Right? And of course, the function f of x has to be continuous, because if it wasn't, then it wouldn't make sense to talk about its limit. So you can't have like a function that sort of goes here, then has a break and goes up here or something weird like that. It's got to be a continuous function. It has to be a continuous function that goes through all these points. And remember, the sequence has an infinite amount of points. So it's not just fitting through the first few. It's got to fit through all of them. That's why it says for all n defined in the sequence. So this replacement theorem, though, is very useful because it tells us that if we can find a function that mimics the sequence at every whole number, then we can analyze the limit as a limit of a function. Analyzing things as a limit of a function allows you to make use of some of the more advanced limit techniques that you learned about, specifically and most importantly, L'Hopital. L'Hopital's rule does not apply to sequences. Because what does L'Hopital's rule involve? It involves the derivative. And when you just have a sequence of discrete points, there are no derivatives because there's no curve. So L'Hopital's rule is completely out in terms of analyzing sequences. But if you can do this replacement theorem, if you can find a function that matches your sequence, then you can make use of things like L'Hopital. And we'll see some examples of that in just a few moments. The other sort of important part of this replacement theorem is it tells you that all of the sort of basic limit laws that you learned about in Calc 1 that apply to limits of functions also apply to limits of sequences. So we're not going to prove these, but I would just like to state them. So these are all the standard limit laws and ideas, and they apply to sequences as well. So for all of these, you have to suppose that an and bn are convergent. If an and bn diverge, then you could theoretically have like an indeterminate form, and you can't make these assumptions or statements. But if an and bn are convergent, so do keep in mind to apply these rules, they do have to be convergent, then these statements apply. The limit of a sum is the same as the sum of the limits. The limit of a constant times the sequence is the constant times the limit of the sequence. So in other words, you can factor constants out of a limit. The limit of a product of sequences is the product of the limit of the sequences. The limit of the quotient of two sequences is the quotient of the limits, provided that the bottom limit isn't headed to 0. And the limit of a sequence to an exponent is the same as that exponent applied to the limit of the sequence, provided that the limit of the sequence is positive and the power is positive. And you have to have these restrictions here because otherwise you could end up with like a square root of a negative number, just not well defined. Also, you probably remember from Calc 1 something called the squeeze theorem, which was a way of sort of analyzing certain limits by squeezing them between two other limits that you knew. And if they squeeze together and trap the other one, then you can conclude that that third limit, the one that's stuck between them, approaches the same place. You can use the squeeze theorem for sequences as well. It works the exact same way that you learned in sort of Calc 1. So this, again, is just something to sort of remind you that when you're working with sequences, pretty much the ways that you approach limits of functions are going to be the same ways that you approach limits of sequences. You just have to remember that a sequence itself is a fundamentally different type of structure. It's discrete as opposed to continuous. So let's go in and start taking a look at actually some computational examples, making sure we actually understand how do we apply limits to sequences. This will also give you just a quick chance to practice sort of understanding analyzing limits. So for each of these sequences, we're going to try to decide if they converge or diverge. For those that converge, we want to state their limit. So we've got 3 sequences here. We want to try to analyze if they converge or diverge. So let's go ahead and take a look at A. Since you have this sequence, what you're really being asked, if you want to know if the sequence converges or diverges, you're being asked to perform the limit as n goes to infinity, 3n squared plus 5n over n squared plus 10. Now, if you think about this, you might say, well, the numerator here as n goes to infinity, this is going to go to infinity, this is going to go to infinity, so this is infinity. And down here, it's also going to infinity. So I might want to use L'Hopital. Well, remember, if you want to use L'Hopital on a sequence, you would have to come up with a function that mimics the sequence at every value. Now, it's not hard to do that here. You could use the function f of x equals 3x squared plus 5x over x squared plus 10. And that is certainly a continuous function that would match this at every whole number. But in general, I would try to avoid using L'Hopital if possible. And there is a way to avoid it here. This is a standard rational sort of expression. You've got polynomial over polynomial. Remember back from Calc 1, the main strategy for doing this was to locate the highest power in the denominator. So we can just simply do an algebraic modification and multiply the top and bottom by 1 over n squared. And I'm choosing n squared because it's the largest power in the denominator. When I do that, I get the limit as n goes to infinity of 3 plus 5 over n, 1 plus 10 over n squared. Why is this so good? Well, because these expressions, constant over n or constant over n squared, as n goes to infinity, these become a number over infinity, which a constant over infinity is always going to go to 0. So this piece here, that's going to go to 0, and this piece here, that's going to go to 0. So this limit then is 3 plus 0 over 1 plus 0, which equals 3. So we could say that a sub n converges to 3. If you want to, you could check that by plugging in some really large values of n, and you will see that when you plug in really large values of n and actually evaluate this, you get numbers that are quite close to 3. Not exactly 3, because this is the behavior as you go to infinity, but close to 3. Okay. So there's analyzing a limit of a sequence. Notice that in terms of technique, even though we're using this letter n, which reminds us that everything is discrete here, the actual analysis is just like how you analyzed limits of functions. Okay, let's try b here. So for b, we have the limit as n goes to infinity of e to the n over n plus 5. All right. For this one, there's no trick like this, because up top you have an exponential, and in the bottom you have a polynomial, specifically a linear here. So this, whenever you have sort of mixed types of functions, in this case exponential and polynomial, this is where you will want to use L'Hopital. So we're going to do what we call a replacement theorem. So we're going to notate that with an RT for replacement theorem, and we're going to analyze the limit as x goes to infinity of e to the x over x plus 5. Now you might say, can't we just always do this? Well, can't we just always plug in x instead of n? I mean, it just looks like we're changing variables. Well, it turns out on basic limits, basic sequences like this, you could think about all of them as some corresponding continuous function. However, in a few minutes, we're going to talk about a very special type of sequence called an alternating sequence that does not have a functional equivalent. So yes, sort of early on, if you really wanted to, you could change every one of these into a continuous function, but that's not the case for every sequence. So again, I really recommend only making use of this replacement theorem when you know first that this is going to work. In other words, that this thing here is really a well-defined continuous function, which this certainly is. And two, you plan on making use of L'Hopital's rule. If you don't plan on making use of L'Hopital's rule, there's no reason to risk using this replacement theorem. For now, though, we can go ahead and use L'Hopital. We can use L'Hopital, remember, because this is an infinity over infinity sort of situation. So L'Hopital allows us to differentiate the numerator and the denominator separately. So we get e to the x over 1. And then, of course, we know that that is going to tend towards positive infinity. So that means the function is headed towards positive infinity. So the function is sort of going up like that. So the discrete values along the way are headed to the same spot. So we would say by replacement theorem, b sub n diverges to positive infinity. And we can specify how it diverges here because we know it's headed towards positive infinity. Okay. Let's try one more here. So we have c sub n equals 2 to the n plus 5 to the n over 8 to the n minus 4 to the n. So we want to analyze this. Again, you might be tempted to go down this route, but this is not a great one to try to use L'Hopital on. Instead, this one is actually more similar to a, because both the numerator and denominator involve the same type of function. All of these are exponentials. Here, everything were polynomials. Here, everything is exponentials. So we do the same trick. Let's locate the largest thing in the denominator. Here, it's not the largest power. It would be the largest base. So let's go ahead and multiply by 1 over 8 to the n, 1 over 8 to the n. If we do that, we should get 2 over 8. Oh, forgot my limit there. Sorry. Let's go back and just erase that. Got to have our actual limit of what we're trying to do here. So limit n goes to infinity of 2n plus 5n over 8n minus 4 to the n. So again, we're using this algebraic manipulation of choosing the largest base in the denominator, similar to how we chose the largest power in the denominator. So when we do that, we get the limit as n goes to infinity. Looks like there's an erroneous mark over here. There we go. And we should get 2 over 8 to the n plus 5 over 8 to the n over 1 minus 4 over 8 to the n. Now, what's so good about this? Well, remember, 2 over 8, 5 over 8, and 4 over 8, those are all numbers less than 1. So, in other words, they're all values that are small. When you take something that's small and you multiply it with itself over and over again, which is what this exponent is going to do, it gets smaller and smaller. Think about that for like 1/2. 1/2 times 1/2 is a fourth, then times a half is an eighth, then a 16th, then a 1/32nd, a 1/64th. It's just going to get smaller and smaller. If you had a big number, something larger than 1, like 2 or 3, those get larger and larger. 3 times 3 is 9, then times 3 again is 27, 81, 243, etc. But when this is a base less than 1, well, it's going to shrink smaller and smaller. So each of these are all going to tend to 0. So we can now say that this is going to be 0 plus 0 over 1 minus 0, which is 0. So we can say c sub n converges to 0. So again, if you wanted to, you could have taken in both a and c, since these haven't introduced anything sort of weird yet, and tried to replace them as continuous functions. In a, if you replaced it as a continuous function and you used L'Hopital's rule twice, you would eventually get it the same result we did here. Notice that ours, though, a lot faster. Here, even if you put it in terms of x and you attempted L'Hopital's rule, exponentials like this will not simplify under differentiation, so it won't help you, and you'll be forced to analyze it the same way. So my big recommendation here in these first couple examples is that you should use this replacement theorem only when you feel like you absolutely must use that L'Hopital rule. If you can analyze the limit algebraically, it is much better to leave the sequence as a sequence and proceed from there. Okay, let's take a look at a couple more examples. So we're going to try to determine if these sequences converge or diverge. And once again, for those that converge, we'd like to state their limit. So let's go ahead and take a look at this one here. So for A, we're going to be looking at the limit as n goes to infinity, cosine of e to the 1 over n. Now, this is a little bit tricky because there's a composition here. We have this exponential with 1 over n in there, and then the result of that is having cosine applied to it. So I want to do this example to sort of give you guys a little bit of a hint, sort of just of a nice way to notate this. The best way to sort of analyze this is to work from the inside out. As n goes to infinity, what happens to this 1 over n? Well, this would become 1 over really large numbers. The numbers get larger and larger. Obviously, that's just 1 over something that approaches infinity. That's going to approach 0. So let's be careful, though, since we're not going to say it's equal to yet. It's just approaching. And let's say that that's going to approach cosine of e. And let's remind ourselves, since we're sort of applying this limit here and saying where this is headed, let's just use a little 0 plus. And what I mean by that is that this exponent is approaching 0, but since n is, positive and we're doing 1 divided by that, it's approaching 0 from the positive side. This notation also just reminds you that this is a limit. It's not yet e to the 0 necessarily. It's just actually a limit. We're just sort of hiding the limit notation. Okay, so what happens to this e as you plug in exponents that are really close to 0 from the positive side? Well, e to the 0 gets closer and closer to 1. So this is going to approach cosine of 1. And again, that would approach it, since we're doing it from 0 plus, as a little from the plus there, meaning things slightly above 1. Now, cosine, does cosine have any weird discontinuities or anything? No. So if you're plugging in numbers close to 1, this just equals cosine of 1. So, of course, cosine of 1 doesn't have a clean value or anything there, but what we just figured out is that our limit is approaching cosine of 1. So a sub n converges to cosine of 1. So we did this just by simply analyzing the composition. Could we have probably just done it from here to here? Sure. If you're really comfortable with limits, you could have just thought about it in your head. You could have said, okay, n going to infinity, this is going to go to 0. E to the 0 is going to be 1. Cosine of 1, well, just cosine of 1. But if you want sort of a nice sort of step-by-step approach, what we're doing is we're sort of applying this limit to the innermost function, keeping this in a notation that reminds us that this is still a limit, then applying the next function, and then finally the last function. Okay, let's go ahead and take a look at b. For b, we need to do the limit as n goes to infinity, ln n squared plus 1 minus ln n cubed plus 2n plus 1. Okay, if we look at this, should be able to sort of see that this is going to infinity here, because as n goes to infinity, the inside goes to infinity, and ln also goes to infinity, and then minus infinity. So this is an indeterminate form, right? Indeterminate form, meaning you can't just conclude. You might say, well, can't we just apply the limit to each of them separately? Well, that only works if they converge and each piece actually diverges here. So we have to sort of reorient ourselves or rewrite this in a way that we can analyze it. The big trick whenever you run into infinity minus infinity is to try to rewrite it as a quotient. Luckily, this is a difference of logarithms, so we can rewrite it as a logarithm of a quotient. So we can view this as limit as n goes to infinity, ln n squared plus 1 over n cubed plus 2n plus 1. Now, in here, we can notice that this is polynomial over polynomial. So let's multiply the top and bottom by the largest in the denominator. So we have ln n squared plus 1, n cubed plus 2n plus 1 times 1 over n cubed, 1 over n cubed. And that looks like we should get the limit as n goes to infinity, ln 1 over n plus 1 over n cubed over 1 plus 2 over n squared plus 1 over n cubed. Okay, what's going to happen with this? Well, this, and this, those are all going to tend to 0 because they're all numbers over something that gets larger and larger. So if we think about this, this is going to be tending towards the ln of, up in here, this is going to be 0 over 1. So this is going to be tending towards ln of 0. Now, Since we're going towards positive infinity and all these things are positive, this is going to be approaching 0 from the positive side. What happens to ln as you approach 0 from the positive side? Well, remember, ln looks like this. We'd be following it down this way. So this is going to approach negative infinity. So we can say that b sub n diverges to negative infinity. So b sub n is a divergent sequence because it's headed towards negative infinity. Notice once again, what we sort of did here is we rewrote it into a form that we were more comfortable with, a quotient. The quotient happened to be inside the natural log, so we analyzed what happens inside, and then we applied the natural log to that result. The inside was actually headed towards 0. ln of 0 is not defined as a value. It's heading towards negative infinity, so we know that our sequence diverges to negative infinity. Okay, we've got one last one here for C. We want to take the limit as n goes to infinity, and looks like we have 3n squared plus 5 over square root 4n to the 4th plus n plus 1. Yep, there we go. All right, we want to analyze this. Let's try the same thing. Let's try to pick out the largest power in the denominator. We might be tempted to call it n to the 4th, but it's not really. There's a square root being applied. Now, square roots don't distribute over there, but if we ignored these, the square root of n to the 4th would actually be an n squared. So let's multiply top and bottom by 1 over n squared. And let's remind ourselves, we'll just sort of note this off to the side, that 1 over n squared is the same as 1 over the square root of n to the 4th. So when we pull this in here, we're going to treat it as an n to the 4th. So this is going to equal the limit as n goes to infinity, 3 plus 5 over n squared, divided by square root 4 plus 1 over n cubed plus 1 over n to the 4th. Now our standard trick that we've seen a bunch of times, each of these terms are going to go to 0. So this looks like we're going to get 3 plus 0 over the square root of 4 plus 0 plus 0, which is going to be 3/2. And notice that I'm safe in writing equals here because I'm getting a number, not something that's going off to some infinity. So we can say C sub n converges to 3/2. Okay, so at this point we've done sort of 6 examples of sequences that converge or diverge and how to analyze them. The big idea here is that pretty much you're analyzing them using the same ideas that you had from when you analyzed limits of functions. One other small note is you will notice that when I'm analyzing the long-term behavior, I'm basically ignoring that starting spot. That starting spot would only be important if you actually wanted to write out what the sequence looked like. Like the fact that this tells us that n is greater than 1 tells us that this starts with like cosine of e, then cosine of e to the 1/2, then cosine of e to the 1/3. It just tells you about the starting spot. But if you're interested in the long-term behavior, the limit, you don't even need to look at this. So this is only written there, and sometimes the book even omits it because it only is just making it more well-defined, right, giving you all of the information. But it's not relevant in terms of determining the limit. Okay, let's wrap up this introduction to sequences by talking about something that is unique to sequences. So far, even though I haven't used it except for once, we could have replaced every one of these with a corresponding function, basically just changing the letter from the discrete n to the continuous x, and analyzed it like that. But we're now ready to talk about something that is unique to sequences, meaning that there's no functional parallel. So we're going to talk about what is called an alternating sequence. And this is very, very important because, again, this is something that is unique to sequences. So an alternating sequence is a sequence of the form b sub n equals -1 to the n times a sub n, where the a sub n is always greater than 0 for all n. So in other words, b sub n is made up of a -1 to the n component, which is often referenced as the alternating piece, and then an a sub n, where the a sub n is always positive. So it's got this alternating piece and an always positive piece that are multiplied together. Why is this -1 to the n referenced as alternating? Well, if the n is an odd number, 1 or 3 or 5 or something like that, then -1 to an odd is -1. But if n is even, -1 to the even is positive. So that means that this alternates, because again, remember, n is a whole number always, it'll alternate between positive and negative. Since the a sub n is always greater than 0, if this alternates between positive and negative, the entire expression always alternates between positive and negative. That's why it gets the name alternating sequence. Let's just look at a quick example of it before we talk about how to analyze it. So, a sub n equals negative 1 to the n, 2n over n plus 2. What does this look like? Well, a sub 1, if we plugged in 1, would be negative, and then you would get 2 over 3. So it would be negative 2 over 3. Then a sub 2, this component would be negative 1 squared, which is going to be positive, and you would get 4 over 4, or I guess 1. Then a sub 3 would be back to this being negative, and you'd get negative 6 over 5. And then a sub 4 would be positive again, and you'd get 8 over 6, or I guess 4/3, so on and so forth. And you would notice that if we actually just wrote it out in the sort of set notation, it does have that property, negative, then positive, then negative, then positive, so on and so forth, right? Now, again, it doesn't matter if the sequence starts negative or starts positive. If I had started this at n is 2, then it would have started positive, but the main idea is that it alternates between positive and negative. You might say, why are these alternating sequences interesting? Why are we actually taking the time to talk about them? Well, it's because these cannot be mimicked by a function, because the function, this minus 1 to the n, there's no continuous function minus 1 to the x, because any sort of non-discrete value, fractional values, minus 1 to different fractions might be undefined, right? If you try to do minus 1 to the x and you had x is 1/2, well, then suddenly you have the square root of minus 1. That's undefined. So there's no way to convert this into a continuous function. It only makes sense because we're just using the discrete values. So this is a unique idea to discrete things, in other words, unique to sequences. So we do have a nice theorem, though, that tells us how to analyze alternating sequences. So an alternating sequence b sub n of this form converges if and only if the limit in absolute value is equal to 0. Well, let's give a visual explanation for that. So here's going to be my sort of drawing here. Okay. So let's imagine up here I'm going to be drawing the b sub n, which is going to be the alternating, and down here I'm going to be drawing the absolute value. Okay. So let's imagine that the b sub n, this guy here, is going to actually converge. So remember, it's supposed to sort of alternate. So let's just draw sort of an alternating sort of piece. So maybe it's here, and then here, and here, and here, here, and here, 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 something like that, right? If our b sub n sort of looks like that, then when we take the absolute value, all these pieces are just going to move up, right? So what we would have then is we'd have something like that, right? If we look at that, we can see that this thing here, this absolute value b sub n, it might be approaching some value. But you'll notice that the b sub n is not approaching anything because it keeps alternating. So if the absolute value isn't headed down towards 0, well, then what's happening is that in the long run, you're oscillating between two different values, and you're not going to converge. Now, if this thing here approached 0, then even though the actual alternating piece would be oscillating, it would be oscillating around 0. So it would be getting closer and closer to 0. So what we can sort of see here is, if we drew a second sort of diagram, let's actually draw the b sub n in absolute value first. If the absolute value of b sub n sort of goes like that, then yeah, this will be alternating. But notice that since this is approaching down to 0, this, even though it's alternating back and forth, is tightening along 0. So in this situation, we would have that it converges, whereas over here, it diverges. So what this basically tells you for this theorem here is that if you want to analyze if an alternating sequence converges, what you do is you analyze its absolute value. If its absolute value goes to 0, then the alternating sequence also converges to 0. And if the limit of the absolute value goes anywhere else, then it's going to diverge. So let's take a look at sort of wrapping this up with just a couple examples of analyzing alternating sequences. So we're going to determine if each of these sequences converge or diverge, and if they converge, we're going to state their limit. So each of these are alternating because you can see they each have this -1 to the end, and then they have a component that is always going to be positive. So let's go ahead and analyze these. For A sub n is alternating. Okay, it's definitely alternating here. So what we're going to do is we're going to say consider the absolute value of A sub n. So now we want to look at the limit as n goes to infinity. If we do the absolute value of A sub n, we put this in absolute value, that's going to remove this, and we're just going to be analyzing this piece. So we'd be analyzing 3n squared plus 5 over n plus 2. Pick the largest power in the denominator, so multiply by 1 over n, 1 over n. That's the limit as n goes to infinity, 3n plus 5 over n, 1 plus 2 over n. This is going to go to 0. This is going to go to 0. This is just a constant, but this piece here, this is going to go to positive infinity. So overall, this thing is going to tend towards positive infinity. So the absolute value tends towards positive infinity. That should tell us that our alternating sequence is going to diverge. So our sequence, A sub n, will diverge. Is ours going to diverge to positive infinity? Well, no, because ours is alternating. It's actually going to be alternating between things really close to positive infinity, and then on the next term, it'll be really close to negative infinity. So it'll diverge by oscillating between plus or minus infinity. In other words, it's going to not have a limit at all. The limit does not exist, because one time you'll be really close to positive infinity, then you'll be really close to negative infinity, then really close to positive infinity, then back to really close to negative infinity. So this one is an alternating sequence that diverges. Okay, let's try B. So B sub n is alternating. So once again, we use the same idea. We're going to consider the absolute value of B sub n. So we're going to do the limit as n goes to infinity. If we do the absolute value here, we're just going to remove that term and analyze the ln of n over n squared. In some ways, what you're doing is you're analyzing the magnitude component. If you've taken like a physics class, right, the magnitude is sort of the size of something. So this is, we're just saying, ignore the alternating part, just focus on the size component. Now, on this here, we've got a logarithm and a polynomial. Those are two different types of functions. So we probably want to use L'Hopital. So we'll do a replacement theorem. You might say to yourself, well, that seems contradictory. Didn't we say that replacement theorem doesn't work with alternating? Exactly. We're not using the replacement theorem on the alternating. We're using it on the absolute value that doesn't have the alternating piece. That's why it's so important that we sort of talked about this theorem here that says to analyze the behavior of an alternating sequence, you analyze the absolute value. By analyzing the absolute value, you're back to things where you can use that replacement theorem. So we're not using the replacement theorem on the actual alternating sequence. We're using the replacement theorem on its absolute value. Now, this is so we can go ahead and use L'Hopital. So this is an infinity over infinity situation here. So we get the limit as x goes to infinity, derivative up top, 1 over x, derivative on bottom, 2x. If you want, you can swing that down in there, and you can see that that is, we'll do it on the next line, that is the limit as x goes to infinity of 1 over 2x squared, and that clearly equals 0. Okay, so we can say by replacement theorem, absolute value b sub n converges to 0. So we now know that the absolute value converges to 0. So b sub n is going to be alternating between things that are really close to 0, so really close on the positive side, then really close on the negative, really close on the positive, really close on the negative. That means, so b sub n also converges to 0. So if the absolute value converges to 0, then the alternating sequence also converges to 0. That's exactly what this theorem said. If the absolute value converges, then the actual sequence converges. Okay, let's do one last one. For C, once again, we have negative 1 to the n, e to the arctan of n. So once again, we have Cn is alternating. So we're going to start by considering the absolute value of Cn. So that means we're going to be looking at the limit as n goes to infinity. If we put this in absolute value, we can ignore this and just focus on the magnitude component. So we have the limit as e goes to arctan of n. Now, what happens with this? Well, this is a composition as n goes to infinity. Arctangent, well, arctangent sort of looks like this. And if you're going towards infinity, you're approaching that pi over 2 asymptote. So this is going to equal e to the pi over 2. Now, we don't know exactly what e to the pi over 2 is. It's like pi is like 3.14, so dividing by 2, you're getting like 1.5 something. So you're raising e to like the 1.5-ish power. So this is just some number. So this tells us that the absolute value of C sub n converges to e to the pi over 2. Now, does this mean that we're done? Well, no. This is the absolute value. So the absolute value converges to e to the pi over 2. Our alternating sequence is going to keep toggling between positive e to the pi over 2 and then negative e to the pi over 2, then positive e to the pi over 2, then negative e to the pi over 2. So those two numbers aren't going to be anywhere near each other. So C sub n diverges by oscillating between plus or minus e to the pi over 2. So again, with these alternating sequences, they are very, very sort of particular. The only way an alternating sequence can converge is if the absolute value converges to 0. That's the only way. If the absolute value goes anywhere else, positive infinity, negative infinity, doesn't exist, equals some non-zero number, then the alternating sequence, because it keeps flipping between positive and negative, will diverge. So this wraps up our sort of introduction into sequences. You now know how to analyze base sequences. You know how to analyze sequences making use of functions through the replacement theorem. And you know how to analyze something that is special only to sequences, the alternating sequence. In our next video, we'll prove a couple theorems about the behavior of sequences that'll help us understand recursive sequences. And then we'll be all done with section 11.1.